Good day, everyone. We are reviewing Wetzel's Limnology textbook, and this is edition number 4. And we are about to embark in chapter 7. And this chapter has about 50 pages on the fate of heat. So this is a very comprehensive chapter, and will take a little while for us to go through it. And this chapter was, edited and created by Sally McEntire with the Department of Ecology, Evolution, and Marine Biology at the University of California, Santa Barbara in the US, and David P. Hamilton with the Australian Rivers Institute with the Griffith University in Nathan, Queensland, Australia. So let's jump right in. So the heating of ponds, lakes, streams, rivers, and wetlands is largely due to the absorption of solar radiation. Heat is distributed via physical processes acting on the water surface at boundaries and within the water bodies, creating density structure in the water column in which organisms live and interact, and in which chemical reactions occur. Thermal structure in individual lakes and flowing waters is dynamic and changes hourly, daily, seasonally, and over longer time scales depending on rates of heating and cooling and the extent of mixing in the water column. Whether lakes and streams heat and stratify or cool and mix is determined by surface energy budgets, which quantify rates of heating and cooling in the upper water, or heat budget, which also accounts for heat gains or losses from inflowing and outgoing streams and rivers, groundwater, and geothermal heating. Thermal structure varies with climate, elevation, morphometry, and optical characteristics. Typical stratification in lakes and ponds, and at times rivers, consist of an upper layer directly influenced by atmospheric forcing, a strongly stratified layer, and a weakly stratified layer below. Depth-dependent stratification is quantified by the buoyancy frequency, and stratification at a whole lake scale is characterized by the Schmidt stability. The sensitivity of lakes to wind-induced mixing across diurnal and seasonal thermocline is quantified by two-dimensionless indices, the weather burn and lake numbers. And the downward flux of heat indicative of turbulent mixing can be used to quantify the coefficient of eddy diffusivity, an index of mixing used for computing fluxes of heat and scalars, such as nutrients and phytoplankton. Annual patterns of stratification have been classified and depend on latitude, elevation, and lake morphometry. These patterns depend on the surface energy budget and the redistribution of heat by physical processes. Distribution of heat in lakes. Brief introduction to thermal structure. Heating and cooling of water in aquatic ecosystem combined with the action of wind on the water surface leads to thermal stratification and mixing over diel, seasonal, and annual periods. As a result, diverse and dynamic habitats are created for organisms, and the biological and ecological effects are wide-ranging. The description that follow apply to lakes, ponds, and reservoirs. In lakes deep enough to stratify during warming periods, thermal structure is typically characterized by an upper, warmer, weakly stratified layer called the upper mixed layer, or epilimnion. It overlays a more strongly stratified thermocline, or metalimnion, with the term thermocline used interchangeably with metalimnion or distinguished as the most strongly stratified region within the metalimnion. If the water column is sufficiently deep, a weakly stratified region of colder and denser water, called the hypolimnion, occurs below. Annual cycles of stratification are characterized by the frequency of periods in which the water column is stratified and by period in which temperatures are nearly isothermal, the same temperature throughout the water column, and characterized as mixing. This distinction can be seen for temperate Lawrence Lake, where the density stratification is stable during summer and winter, and temperatures are near isothermal in spring and autumn. In summer, the warmest temperatures are near the surface. In winter, when ice forms and water temperature are less than 4 degrees centigrade, the temperature of maximum density in freshwater, the water is coolest near the surface and warmer below. The temperature profile is then characterized as inversely stratified. This distinction of periods with stratification and mixing belies the dynamics that occurs within lakes, as can be seen in figure 7-4, the upper mixed layer is increasing and decreasing in depth during the summer, indicating mixing within this layer. And while sometimes the water body is mixing when temperatures are near isothermal, at other times it is not. Lakes such as Lawrence Lake, with 2 periods annually in which stratification occurs over the full water column, and 2 periods when temperatures are nearly uniform throughout, are classified as dimectic, a common classification for moderately deep and deep lakes in temperate climates. Annual patterns of thermal stratification for lakes at different latitudes and of different sizes are described in section 2C. High-resolution instrumentation and more frequent sampling indicate more complex and dynamic structures in the upper mixed layer and hypolimnion than implied in earlier descriptions. Over diel cycles, solar heating tends to exceed heat losses such that warmer, less dense water is found near the surface. At night, heat losses dominate, eroding stratification which developed in the day. For example, a temperature profile taken midday during light winds in a warm season would have a near-surface weakly stratified upper layer called the surface layer, or actively mixing layer. A layer with a larger temperature change below a diurnal thermocline, a weakly stratified region below called the subsurface layer, a persistent region with a larger temperature gradient called the seasonal thermocline, and depending on the depth of the lake and the penetration of light, a weakly stratified deeper layer called the hypolimnion. So let's look at figure 7-1. So first, on the x-axis, we have the lake bottom, and then on the y-axis, we basically have the lake profile. So we have wind, let's say that is moving from west to east, assuming west is to our left and east is to our right. And we have also the sun that is acting upon the water surface by heating it, or the absence of sun, cooling it. Then we have different depth, and then we have the temperature profile right here. So the first depth that we have here is a turbulent wind convection influence depth. Then we have the intermittently turbulent shear depth, and then we have the intermittently turbulent depth with no shear. And so according to the section we just read, we have the actively mixing layer here, we have the diurnal thermocline, which happens during the day, during a typical day, and then we have the subsurface layer, and then we have the seasonal thermocline, and then if the lake is deep enough, we have a hypolimnion. And so the temperature is pretty stable throughout the hypolimnion. It starts to increasing a bit, then it goes through a phase where it's stabilized as well through the thermocline. Then we also have an increase here in this subsurface layer, and then stabilization in the thermocline, and then pretty much an increase here, right here, to a stable temperature all the way to the surface. So the sketch of a temperature profile in a lake during the day, showing the various layers which form and whether they are likely to be turbulent and mixing, or intermittently turbulent as opposed to laminar, not mixing. The vertical axis is the depth with z prime, the distance downward from the surface. And the actively mixing layer, the diurnal thermocline and subsurface layer, comprise the upper mixed layer, also known as the epilimnion. And the seasonal thermocline and hypolimnion are below it. So the epilimnion is right here. The actively mixing layer is also called the surface layer, and its depth here is identified as HM right here. Its depth and that of the diurnal thermocline varies over the course of a day. This is why we call it diel, D-I-E-L. The horizontal lines labeled diurnal and seasonal thermocline respectively bisect the layers where temperatures rapidly decrease with depth. The diurnal and seasonal thermocline are also intermittently turbulent. Figure 6-2 is an example, so A is an example of a mooring design to obtain time series temperatures. So I'll let you look into that. And as for, let's see here, as for B, we have, looks like a temperature and depth profile for a lake. And I'm not seeing it in here. but census position in Lake. So this is Lake Rotorua on the North Island in New Zealand at 4 times a day on 5 February 2017. So these measurements were taken at that lake and show the temperature profile on the x-axis and the depth and the various thermocline that we have. We have the diurnal thermocline, the upper one, and then the seasonal thermocline, the one below that. So this is seasonal, this is diurnal. And this is the epilimnion, and then it looks like there is an apolimnion on that lake. The extent to which these layers are turbulent depends on the magnitudes of winds, heating and cooling. If winds are light during a period of heating, the diurnal thermocline may reach the surface. With stronger winds or onset of cooling, mixing can lead to the development of a surface layer that is near isothermal. And with continued cooling, this upper layer may deepen, potentially reaching the seasonal thermocline at night or when winds are strong. Such changes over a diel cycle are illustrated for a lake in New Zealand, figure 7-2, and the changes in the depth of the layer of a diel cycles are illustrated in figure 7-3. The density structure that develops in the day moderates ecosystem function. For instance, it influences the extent to which phytoplankton are mixed and the light they receive, as well as the efficacy of grazing by zooplankton. The depth of the upper mixed layer, diurnal and seasonal thermoclines and apolimnion vary with heating and cooling and with changes in wind velocity and direction, such that the depth of these layers can vary along the length of a lake. High-resolution temperature profiles often show temperature steps within the thermocline and apolimnion, with these steps related to internal wave motions. No strict definition of a thermocline based on temperature change is appropriate given the nonlinearity of the curve relating temperature to density, and the variable heating, cooling, and magnitudes of wind over lakes. Hence, in some water bodies, the temperature change across the thermocline may be a few degrees Celsius per meter, whereas in tropical lakes, it may be only a few tenths of a degree per meter. The apolimnion is sometimes divided into 2 layers, a near bottom one called the bottom or benthic boundary layer, where stratification is weaker and more mixing occurs, and a quiescent layer above where stratification is slightly stronger. These authors, in fact, proposes a 3-layer classification scheme with surface and bottom boundaries layers that frequently mix and quiescent interior. In their scheme, the thermocline and upper hypolimnion would comprise the interior layer. These distinctions point to the dynamic nature of thermal structure over diel to annual periods. So let's look at figure 7-3 here. So this is your typical diel structure. So this is over a course of a day from sunset to sunset, and this is the sunrise. So this is where the sun is above the horizon, and this is the sun when the sun sets. So the same here, we have a sunset to sunrise, so that means this is night time and this is daytime. On the y-axis, we have the depth. So this is the air-water interface. This is the top of the seasonal thermocline here. And then here, as illustration, we have penetrative convection and wind drive entrainment. Then we have heating suppresses turbulence and sets up density stratification. And then lastly, we have wind drives entrainment. So over the course of a day, we may have wind driving how thermally a lake behaves. So layered structures within the upper mixed layer and their changes over diel cycles. The actively mixing layer is above the diurnal thermocline and the subsurface layer is below it. The diurnal thermocline forms in the day during heating. If heating is ongoing, it may deepen in the afternoon from wind-induced mixing. As the lake begins to cool, both penetrative convection and wind-induced deepening continue at night. The diurnal thermoclines were formed after sunrise with increased heating. ZAML indicates the depth of the actively mixing layer. During stormy periods, the entire upper mixed layer may be an actively mixing layer not shown. So here we have the diurnal thermocline, and then here as well, the diurnal thermocline, and the way it changes through time from sunrise to sunset, and then from sunset to sunrise here. And so what we see is that at night, that diurnal thermocline is lowers, is at a lower level than during the day. And we can see also as the sun starts to go below or start to go nearing the horizon, beyond the zenith, we can see a decrease in the thermocline as there is less heating impinging upon the lake. Annual cycles of heating and cooling in lakes demonstrate patterns dependent on latitude, local climate, optical conditions, and lake depth. For example, Lawrence Lake, a small shallow lake in Michigan, was ice covered from December through March, with temperatures increasing from the surface downward. With the coldest temperatures immediately under the ice, the lake had inverse temperature stratification. Following ice off, temperatures were nearly isothermal at 4 degrees centigrade. The temperature of the maximum density of fresh water. Temperatures rose with increased solar radiation entering the water, and thermal stratification developed by May. Several periods with heating and cooling occurred in summers, such that the upper mixed layer had the structure evident in 7-1, and the changes over diurnal cycles as in figure 7-2 and 7-3. By August, as incoming solar radiation declined, the mixed layer began to deepen, and the lake was isothermal by November. This period is called fall turnover. As with near surface temperatures cooling, water near the surface becomes denser, causing mixing. The term turnover is applied when the water column becomes isothermal. Although high-resolution instrumentation indicates isothermy is rarely sustained. Ice-on occurred when temperatures in much of the water column had declined to approximately 3 degrees centigrade, so above freezing, and were near zero at the surface. The patterns in Lawrence Lake are representative of lakes in regions with cold winters and warm summers. Given the variability in climate as a function of latitude and altitude, methods to quantify heat budgets in lakes are described in section 1b and in streams and rivers in section 1c. Indices derived from heat budget indicates the susceptibility of lakes to mixing are described in section ID, etc. So I'm not going to go through that. You can just read that and see where that content is found, and you can also look at the table of content, of course. So this is actually a very common diagram that we see very often in limnology, and that shows three kind of items here, parameters. So the first one, as we saw before, on the y-axis we have depth in meters, and then on the x-axis here we have the month. So this is for an entire year. This is in 1968, and then these curves represent temperatures, isothermal temperatures. So for example, in January, at that depth, at 12 meters, the temperature was 3 degrees centigrade, right? And then it was 4 degrees starting in early February. And it stayed at that depth, it stayed there. And then you can see that during that time that the lake was pretty well mixed, that the temperature was about the same. And as we saw in the text, as we approach the surface, and you can see that a little bit with the density of this line, the lake became ice-bound. There was ice on the surface of the lake. So the temperature decreased slightly. So the warmest temperature, interestingly enough, in the winter are our depth compared to the surface. And that is the opposite in the summer. So let's look at the summer here. We have very high temperatures in the 24 degrees centigrade right at the surface, and then we have colder temperatures here at depth in the lake. And so then we can see that stratification is starting to develop from an isothermal value to temperatures with distribution, because we don't see that in the winter. We have now 8 degrees, 9 degrees, 10 degrees, etc. So for example, if we take early May, we have probably 7 degrees here, right at the bottom, 8 degrees at 10 meters, 9 degrees at 8, 10, etc. And so this is, I recommend that you kind of become familiar with this, because you will see that very often, and it's so very informative about how our lake temperature distributes through time, as well as depth. So let's see. And so then bracken region on the surface, so we talked about that. And then the dotted line shows the depth of the upper mixed layer. Immediately below the upper mixed layer, the thermocline can be discriminated by abrupt temperature changes, but the full region below the upper mixed layer is characterized as a metalimnion due to the relatively strong stratification. So in this case here, in this lake, we don't seem to have a hypolimnion. We only have an epilimnion and a metalimnion.